Our goal in this lecture is to prove Kolmogorov's extension theorem, constructing an infinite-dimensional probability measure on the sequence space from a consistent family of probability measures on the finite-dimensional Euclidean spaces embedded within it. In order to get there, we first need an intermediary step about regularity of probability measures on Euclidean space. Given any nice topological space, nice in this case means locally compact Hausdorff space, but you can just take Euclidean space as the model that we need to consider, a measure on the Borel sigma field of that space is called outer regular if the measure of any Borel set is equal to the infimum of the measures of all open sets that contain that Borel set. It is called inner regular if the measure of any Borel set is the supremum of the measures of all compact sets that are contained inside the Borel set. Now this should sound a little familiar. Going way back to lecture 4.2, what we really did was to show that the outer measure of a Borel pre-measure is outer regular on the Lebesgue sigma field, that is, on the completion. We're going to show that actually all probability measures on Euclidean space are inner and outer regular. That is to say, we're going to show that they're all radon measures. Now, we already defined radon measure to be something that includes all probability measures on Euclidean space, so we should really call this a redefinition. A Borel measure on a locally compact Hausdorff topological space is called properly a radon measure if it is locally finite, that is, it assigns finite measure to every compact set, and it is regular. It is both inner and outer regular. Now, the reason why we didn't include those conditions in the definition of radon measures when we introduced them on the real line is because of this theorem that we're about to prove. All finite Borel measures, in particular Borel probability measures, on Euclidean space are in fact radon measures. They are inner and outer regular. We're going to prove this for Euclidean space, but actually with almost no tweaking, the same proof works for all Polish spaces. That is, the theorem is that for any complete separable metric space, all Borel probability measures are regular. The proof of this has the flavor of other proofs that we've given for extensions using something like Dynkin's multiplicative systems theorem, although we're going to approach it much more directly than that. Here's the idea. We define a set F of subsets to be the set of all Borel subsets with the property that they can be well approximated from the outside by open sets and from the inside by closed sets. That is, it's the set of all Borel sets with the property that for any tolerance epsilon, there's an open set V and a closed set C that nest our set B such that the measure of the difference between V and its subset C is less than epsilon. We're going to show that that collection of subsets is actually the full Borel sigma field. And that suffices to prove the theorem. To see that this implies outer regularity, notice that if C is contained in B is contained in V, that means that V minus B is contained in V minus C. And since V minus C can be made small in measure, that means that we can find a sequence Vn of open sets containing B such that the measure of Vn minus B is less than 1 over n. Now, since mu is a finite measure, that difference is the measure of Vn minus the measure of B. And that says that we can find an open set Vn whose measure is less than the measure of B plus 1 over n. That shows that the infimum over all open sets containing B is the measure of B. Now, a similar argument based on the containment of C in B shows you that the measure of B is the supremum of the measure of all closed sets that are contained in B. But the property of inner regularity is about compact sets, not closed sets, and we're working in a space like RD that is not compact, so we have to be a little careful here. So by a very similar argument to the one we just made for open sets outside, we can find a closed set Cn for each n, such that the measure of B minus the measure of Cn is less than 1 over n. And that shows us that the measure of B is the supremum over the measures of all closed sets that are contained in B. Now to get to compact sets, we note the following. Take the closed balls in Rd, or in our complete metric space if we like, of radius n. As n increases to infinity, those fill out all of Rd. And therefore, if I take the intersection of those closed balls with our closed set C, those increase to C. Now, the closed set C is closed, and the closed ball in Rd is compact, and therefore their intersection is a compact set. And so I can approximate any closed set by compact sets. And now by the continuity of probability measures, I get that the measure of that intersection increases to the measure of C. And so if I can approximate B by closed sets inside, I can approximate it by these compact sets inside just as well. Thus, in order to prove this regularity theorem, it suffices to show that this collection of subsets is the full Borel sigma field. We're going to show that this collection F is a sigma field that contains all closed sets. That means that it contains the Borel sigma field, which is the sigma field generated by all closed sets. So we'll do that in a few steps. First, we'll show that F contains all closed sets. Well, if C is a closed set, consider its epsilon neighborhood. That is, the set of all points that are distance at most epsilon away from some point in the closed set C. Now that epsilon neighborhood C epsilon is open, since it is a union of open sets. And moreover, as epsilon decreases to 0, that set closes in on C. I'll leave you to work out the details. That's a simple topology lemma. In general, the epsilon neighborhood of a set closes in on its closure. But since C is closed, we close in on C. Therefore, by the continuity of measure, the measure of C epsilon minus C decreases to 0. And so that means that we can take C, which contains the closed set C, and is contained in C epsilon, which is open, and we can make the measure of the difference between this enclosing set and this inside set as small as we like, which shows that the set C is in F. Now we need to show that F is a sigma field. We'll first show that it's an algebra, and then show that it is closed under countable union. In fact, countable disjoint union, which will be enough once we know it's an algebra. So, to see it's an algebra, we just verify step by step. The empty set is indeed in F, since the empty set contains the empty set and is contained in the empty set, which is both open and closed, and the measure of the difference between the empty set and the empty set is as small as we like. Now, suppose we have some set A in this class F. That means that we can find an enclosing open set and an inside closed set whose difference has measure less than epsilon. We'd like to show that a complement can also be so enveloped. Well, just using De Morgan's laws, notice that the complement of A is contained in C complement and contains V complement. The complement of a closed set is open, the complement of an open set is closed. And the difference between C complement and V complement, which is C complement intersected with the complement of V complement, is C complement intersect V, which is the same thing as V minus C. And so therefore, the measure of C complement minus V complement is the same as the measure of the difference between V and C, which by assumption is less than epsilon, and that shows that we can enclose a complement appropriately, and therefore a complement is contained in F. Similarly, if I have two sets, A1 and A2, that are in F, I can enclose them with an open set on the outside and a closed set on the inside, such that the difference between those two each has measure less than epsilon over 2. Then we'll just do the sort of follow your nose thing and let C be the union of the two inside closed sets. Being a finite union of closed sets, it is closed. That is contained in A1 union A2, which is contained in V1 union V2, a union of open sets which is open. Let's call that V. Then the measure of V minus C, which is the measure of V1 minus C union V2 minus C, is less than or equal to the measure of V1 minus C plus the measure of V2 minus C. But C1 and C2 are contained in C. And so if I remove the smaller sets, C1 or C2, instead of C, I can only increase the measure. So that's less than or equal to the measure of V1 minus C1 plus the measure of V2 minus C2, which is by assumption less than epsilon over 2 plus epsilon over 2. And therefore, V and C do the trick. And we see that the union of A1 and A2 is back in F. And so we have verified that F is an algebra of sets. Finally, to show that F is a sigma field, we will show that it is closed under countable disjoint unions. So suppose that we have a disjoint collection AN of sets in F. That means each AN can be enclosed by a VN on the outside and a CN on the inside, with difference having measure as small as we like. So let's do our typical summability trick and make it less than epsilon over 2 to the n plus 1 in this case. Now we'd like to say, hey, the union of the ANs is contained in the union of the VNs and contains the union of the CNs, and it'll all work out just like it did in the last case with a finite union. And that's true, but there's one troubling point there. The countable union of the CNs need not be closed. So we have to work a little bit harder there. Let's instead take the union of the first capital N CNs and call that Dn. Now, since it's a finite union, it is closed. We can take the union of all of the VNs, that will be open. And then note that the disjoint union of all the ANs is contained in that union of VNs, which we'll call V, and it also contains Dn for every n. So we have a closed set and an open set enveloping it, as we hope. And so we'll do the same trick we did before. The measure of V minus Dn is going to be less than or equal to the sum over all of the VNs, the measure of Vn minus D capital N. Now let's break up that sum for the first n and the remaining ones. For the first n, where we're removing a D capital N, the D capital N is the union of the CNs, so each one of them is contained in Dn, and so we can only increase the measure if we remove instead just a Cn. And when we get beyond capital N, we just won't remove anything at all and say this is bounded above by the measure of Vn. Now, by our assumption, this measure is less than epsilon over 2 to the n plus 1, and by a calculation similar to the one we did on the first page, this measure is less than the measure of an plus epsilon over 2 to the n plus 1. So putting together those epsilon over 2 to the n plus 1s over the whole sum, and noting that the sum, n going from 1 up to infinity, of epsilon over 2 to the n plus 1 is epsilon over 2, we get that this whole thing is less than or equal to epsilon over 2 plus the sum, little n going from capital N plus 1 up to infinity, of the measure of an. Of course, this last term here is the measure of the disjoint union, n going from capital N plus 1 up to infinity, of an, because those are disjoint sets. Now this estimate is valid for any capital N. As capital N goes to infinity, this disjoint union closes in on the empty set. And therefore, by the decreasing continuity of finite measures, this tends to 0 as capital N goes to infinity. Therefore, we can choose a capital N large enough so that this is less than epsilon over 2. And putting that all together, we have found our enveloping sets, concluding the proof. So we now know that all probability measures on Euclidean space are regular. We're going to use that regularity in a fundamental way in our proof of the Kolmogorov extension theorem. So remember our setup. We have our infinite cube, Q, which is the sequence space of all sequences taking values in the unit interval. We equipped it with the topology of pointwise convergence. And with respect to that topology, we showed last time that it is a compact topological space, which therefore has the finite intersection property. If I have any sequence of closed subsets of Q, such that the intersection of any finite number of them is non-empty, then the intersection of all of them must be non-empty. We're going to use that in a fundamental way in the proof of the Kolmogorov extension theorem right here. The theorem says that if I have a sequence µn of Borel probability measures on the n-dimensional cubes that satisfy this consistency condition, the n+1th measure, when restricted to the n-dimensional cube embedded inside the n+1 dimensional cube, is equal to the nth measure in the sequence. Then there exists a unique probability measure P on the entire Borel sigma field of the sequence space of the infinite cube, such that its restriction to any finite dimensional cube embedded inside the full space is the appropriate dimension, measure µn, from the consistent sequence that we started with. Before we proceed to the proof, let's look at an important special case to demonstrate how we're going to use this. Suppose that our measure µn is a product of one-dimensional measures. Then the n+1th measure, which is the product of the first n and the n+1st, is the product measure µn, product with μn+1. And that means that μn+1 of any n-dimensional Borel set times the full unit interval is, by the rectangular law for product measures, µn of b times μn+1 of the whole unit interval. But that is, of course, 1, because μn+1 is a probability measure, and so we do indeed get the consistency condition. This is by no means the only way you can achieve such a consistent sequence of probability measures, far from it, but it is the way we will use the Kolmogorov extension theorem to construct infinite product measure. So let's proceed right into the proof. We're going to let scripty Bn be the set of all subsets of the cube of this form. A Borel set on the n-dimensional cube times all values of the rest of the coordinates. Now it's an exercise for you to verify that that is exactly the sigma field generated by the first n projections. That is, we have the standard projections from the sequence space into the base unit interval, where pi k of a sequence is just the kth component of that sequence. So this is a sigma field, and it is in fact this sigma field here. Now let's take the union of those sigma fields, which, as we know, is typically not a sigma field, but it is, however, an algebra of sets. In fact, this algebra generates the full Borel sigma field of the topological space Q. Why is that? Well, the sigma field it generates is, of course, a sigma field, and we'll show that it contains all closed sets. If C is any closed set in the cube, take its projection onto the n-dimensional space, that is, the product of the first n one-dimensional projections. Projections are closed maps. Their images are closed, and so this is a closed set in the n-dimensional cube. Now, if we take the product of that n-dimensional closed set with the rest of the coordinates, that is, with the cube itself, that's this pre-image here, and it's easy to check, again, because C is closed, that the original set C is the intersection of all of those extended projections. But that means that that closed set is in the sigma field generated by the first n projections for every n. And that means that it is in the sigma field generated by their union. So that shows that all closed sets are contained in the sigma field generated by A, which means that the sigma field generated by A is the full Borel sigma field of the infinite cube. Now our goal is to show that there exists a probability measure on this Borel sigma field with the stated condition right here. So we're going to prove that by just declaring it to be so and showing that that's well defined. In other words, we're going to define a function p on this algebra, which is the union, the increasing union of these sigma fields. So every element in this union has the form b times q for some b in some finite dimensional Borel sigma field. And for any such element, a times q, we define the p measure of a times q to be nu n of the finite dimensional part, where n can be picked off from whatever the dimension of this a is. Now the first thing we need to do is verify that that makes any sense at all. We need to see that this is well defined. And that is exactly what the consistency condition on the sequence of measures nu n is all about. That is on your homework, to show that the consistency condition implies that this is a well-defined formula and in fact defines a finitely additive measure on this algebra of sets. So going way back to the beginning of this course, if we want to show that p extends to a measure, what we need to do is show that it's more than just finitely additive. We need to show that it's a pre-measure on that algebra of sets. We need to show that it is countably additive or continuous over countable sequences of increasing sets in the algebra A. If we can show that, then we know that it has a unique extension to a measure p bar on the closure of A in the pseudometric sense, or in the Cartier-Dori sense, or in the null completion sense, since all three of those are equivalent. And then we can just take our blackboard bold p putative measure to be the restriction of that closure to the sigma field generated by A, which is certainly inside here, since this is a sigma field containing A, but that we know is the desired Borel sigma field. And then we need to show that this condition, which we only assumed held on the algebra, actually holds on the full sigma field generated by the algebra. But once we know that p extends to a measure, proving that is a simple matter of applying something like the monotone convergence theorem, as I'll let you readily verify. So that means that all we have to do is show that this p is a pre-measure. Since it's finite, it suffices to show that it is downwards continuous, meaning that if I have a sequence an of sets in the algebra A that decreases to the empty set, then this finitely additive measure p of an must decrease to 0. Now we're going to show the contrapositive of that. We're going to show that if we have a sequence bn of sets in A that decreases to something, b, such that the infimum of the measure p of those bn's is not 0, is some strictly positive number epsilon, then that intersection b is non-empty. And here is where the finite intersection property from Tikhonov's theorem will come in handy. Now, the first claim, to simplify this, is that the bn's, which are assumed to be in the union of the scripty bn's, which is an increasing union, can be assumed to actually match up where bn is in scripty bn. To see that we can make this restriction without loss of generality, notice that if we choose any bn in the algebra A, which is this increasing union of the scripty bn's, that means, by definition, that bn can be found in some scripty b mn, for some large mn. That does not mean that bn is necessarily in scripty bn, of course. What we're going to do is replace the sequence bn with a different sequence that is. To do that, we'll just write out these indices mn. Here's m1, here's m2, etc. And then we'll define a new sequence, b twiddle k, like this. So b twiddle 1, 2, up to m1 minus 1 are all just the whole cube, and then switches to b1 at m1. And then it stays constant at B1 until we get to M2, which is the first place that it switches to BM2, and so on. We just stretch out and amplify the sequence Bn so that the indices match. Now, we're just going to replace the original sequence Bn with the new sequence B twiddle k, and it's fine to do that because B twiddle k has all the same properties. B twiddle k is a decreasing sequence. Since the original sequence is, it just decreases a little bit slower. And the infimum of the finitely additive measure P of the BKs is easily seen to equal the infimum over n of the measure of the BNs, which is epsilon. And the intersection of all of the B twiddle Ks is the same as the intersection of the BNs. These are all statements that you can easily verify. And so having found our BNs, we'll just replace that sequence with the B twiddle Ks, except we'll still call it Bn going forward. And so without loss of generality, we may as well assume that Bn is in scripty Bn. Well, that means that Bn has the form Bn prime, which is a Borel set over the n-dimensional cube, times Q. Now we use the inner regularity of Borel probability measures on the unit cube, for example. We can find some compact set, Kn prime, inside Bn prime that approximates it really well. That is, such that the new n from our sequence of Borel measure of Bn prime with Kn prime removed is less than epsilon over 2 to the n plus 1. Now we'll let Kn be the amplification of Kn prime. That is, we take Kn prime multiplied by the cube so that this is back in the Borel sigma field over the whole infinite cube. And by our well-defined definition of P, since P restricts to nu n in the appropriate fashion, we get that this difference is less than epsilon over 2 to the n plus 1. Let's also note that since this is a closed set, and since the topology on Q is the topology of pointwise convergence, this Kn is a closed set inside Q. So to sum up, what we've shown is that if Bn is any sequence of sets in scripty Bn, we can find closed sets in Bn of the appropriate form that approximate Bn from the inside this well. And that means following the same kind of calculations we did when verifying the regularity property for Borel measures. The P measure of Bn minus the intersection of the first n of these Ks, which by De Morgan's laws is equal to the probability of the union of Bn minus Ki, by subadditivity, which follows from the finite additivity of P, that's less than or equal to the sum of the P measure of Bn minus Ki. Now, the Bn's are a decreasing sequence. That means that this Bn here is the smallest among all of the Bi's up to n, and so if I replace Bn with Bi, I can only increase the measure. But by construction, this is less than epsilon over 2 to the I plus 1, and that sum is less than epsilon over 2, because we can take n equal to infinity here and get exactly epsilon over 2. But remember, our initial contrapositive assumption was that the infimum of the P measure of all the Bn's was epsilon. Thus, the P measure of that intersection of the first n Ks, which we can somewhat amusingly write as Bn minus that intersection, is P of Bn minus P of Bn minus that intersection. This is epsilon, this is less than epsilon over 2, and so this whole difference is greater than epsilon minus epsilon over 2, which is strictly positive. But P is a finitely additive measure, which means that P of the empty set is 0, and since the P measure of this set is not 0, we can conclude that that intersection of the first n Ki's is not empty for any n. Those Ki's are closed sets, as we established, and therefore, by the finite intersection property that the infinite cube has, the intersection of all of the Ki's is non-empty. but the ki's are contained in the bi's. And so that shows that the intersection of all of the bi's is not empty, which is exactly what we were trying to show. And therefore, by contraposition, we have established that P is a pre-measure and therefore extends to the probability measure that we need, concluding the proof of Kolmogorov's extension theorem. Now, as we noted immediately after the statement of the theorem, this will allow us to construct something like infinite product measure if we take our sequence of consistent measures nu to be finite product measures. But the way we've set things up, those would have to be measures on the unit interval. So the first thing we want to do now is abandon the unit interval. We set things up for the proof of Kolmogorov's theorem to use it because it's a compact set. But now we can expand beyond the compactness, now that we've used compactness where we need it. So for the sake of simplicity, let's just consider the real line, although we could really do this on Rd or on any set which is measure equivalent to a Borel subset of the unit interval, which is a large collection of sets called regular Borel spaces. Let's consider the full sequence space now, R to the n of all real sequences. As usual, we have our standard projections that pick out the components of our sequences. We take script EBn to be the sigma field generated by the first k of those projections, and script EB to be the sigma field generated by that increasing union of sigma fields Bn. Then the theorem is, just like in the statement of Kolmogorov's theorem that we just gave, if I have any consistent sequence of probability measures on Rn as n increases, then there exists a unique probability measure P on the full sequence space equipped with this Borel-like sigma field that restricts to those measures on the finite dimensional embedded subspaces. And the proof of this is simply by equating the real line with the open unit interval. Fix any homeomorphism. For example, we could take an arctangent function. Actually, since this is a probability course, it would be nice to consider an alpha of the form integral from -infinity up to x of f of t dt, where f is a strictly positive, continuous probability density. That will give such a smooth homeomorphism here. We could, for example, take f of t equal to 1 over pi times 1 over 1 plus t squared, and that would give us our arctangent type function that I alluded to. Well, then it follows that the n-fold product of that is a homeomorphism from Rn into the n-fold product of the open interval. And since it's a homeomorphism, that means that a subset B of Rn is a Borel set, if and only if its image A under that homeomorphism is a Borel set in the open cube. But we can identify the open cube as a topological subspace of the closed cube, and therefore identify the Borel sigma field as a subsigma field thusly. And so we will use this homeomorphism to push forward the measures nu(n) on the real space to measures on the cube as follows. Nu(n) twiddle of a set A in the closed unit cube will be the push forward of nu(n) applied to the set A intersected with the open cube. And I'll leave it to you to verify that this is a Borel probability measure on the closed unit cube. We can also easily verify by the nice functorial properties of the push forward, which I will spare you the details of, that this sequence has the desired consistency condition. And therefore we can apply Kolmogorov's extension theorem to the sequence nu(n), but we can then untwist it to see that the same results apply to the sequence nu(n). And you can work out all of those details on the back of an envelope while you're bored this evening, if you like. Now that means that we can construct infinite products of probability measures on the real line, which is what we need to do, finally, to construct IID sequences with prescribed laws. So that's our final result for this lecture. Let mu(n) be a sequence of Borel probability measures on the real line. then there exists a probability space, omega fp, and a sequence xn of Borel real-valued random variables on that probability space that are independent and whose laws are given by those prescribed measures for all n. And the way we do that is to take our putative sample space to be the full sequence space. We take F to be the Borel sigma field generated by all of the projections, what we called B on the last slide, which, by the way, we will henceforth identify as the infinite product sigma field of the Bn's, which were themselves the sigma fields generated by the first n projection maps. Then we define a sequence of measures nu-n to be the product measure of the first n measures mu1 through mu-n. Then, as we verified on the slide where we introduced Kolmogorov's theorem, we can easily check that these product measures satisfy the consistency condition that we need them to satisfy. And so we can apply Kolmogorov's theorem here to find a probability measure P on this infinite product sigma field, which restricts to these product measures on the appropriate embedded finite dimensional subspaces. How does that help us? It helps us because we can now do exactly what we did at the very beginning of the last lecture and construct our independent random variables as the projection maps. Taking xn equal to pi n, it is clearly measurable with respect to the sigma field generated by those projections. And if we fix b1 through bn Borel sets over the real line and ask for the probability under this constructed infinite product measure that pi 1 is in b1 through pi n is in bn, well, that's just by definition the probability of pi 1 inverse of b1 intersected with pi n inverse of bn, which is, by the definition of the projections, simply the measure of the product b1 up to bn times all other coordinates being unconstrained. Well, by Kolmogorov's theorem and the basic property of this probability measure, that is equal to nu-n of just the first n component part. But nu-n is the product measure of mu1 through mu-n, and so by definition, that's mu1 of b1 times up to mu-n of bn. But doing the same trick we did in the finite dimensional case, and taking each of the bn's equal to all of r except for one of them, we see that each one of these is also the law of pi n. And so in one fell swoop, that shows that the pi n's are independent and have as their individual laws the prescribed measures we started with, which shows that we can construct independent sequences with prescribed laws. In particular, we have IID sequences. Next time, we're going to start investigating in more detail the structure of this sigma field and the sub-sigma fields generated by the projections in the tail.